Hello everyone. In this video, I will explain the convolution of analog signals using Python. I will walk you through the code step by step so it's easy to understand even if you're new to signal processing. We knew the convolution describes how an input signal interacts with a system to produce an output, and mathematically, this is written as y of t is equals to x of t times h of t. First, import the necessary libraries, NumPy for numerical computations, Matplotlib for plotting the signals, and the convol function from SimB, which allow us to compute convolution efficiently without manually implementing the convolution integral. Next, I define the time axis using linspace from -5 to 5 seconds with 1000 points. This very small spacing between points allow us to approximate continuous time or analog signal using discrete sample. After defining the time axis, I define the first signal x of t. Here, I use a conditional statement so that x of t has a value of 1 only between t equals to 0 and t equals to 2 seconds, and a 0 elsewhere, which represent a rectangular pulse with a width of 2 seconds. This signal can be thought of as our input signal. Then I define the second signal h of t, which is an exponentially decaying function multiplied by condition that is ensures it only exists for t greater than or equal to 0. This represents a causal system, since a system does not respond before the input is applied. Next, I perform a convolution. I first compute the time step of dt from the time array, which is important because continuous time convolution is an integral, and multiplying by dt allow us to approximate that integral correctly. Then I use the convolve function in full mode so that the entire convolution result is captured, including the parts where the signals only partially overlap. Since convolution increases the signal duration, I also define a new time axis for the output signal so that the result is plotted correctly in time. Finally, I plot the results using the three subplots. The first plot shows the input signal x of t, the rectangular pulse. The second plot shows the impulse response h of t, the exponential decay, and the third plot shows the output y of t, which is the convolution of x of t and h of t. All plots are clearly labeled with titles, axis labels, and grids to make them easier to interpret. Now, looking at the output plot, we can see that the rectangular input signal is transformed by exponential impulse response. At first, the output rises as the exponential response accumulates with or while the pulse is active, and after the pulse ends, the output gradually decays due to the exponential nature of the system. This clearly demonstrates how convolution describes the effect of a system on an input signal, making it a powerful tool for analyzing linear time invariant system in analog signal processing.